Hello, physics. Welcome to this week's lesson on wave parameters. This will be a nice start to what we will cover next week or in the next lesson. Looking at waves, these are going to be oscillating phenomena. And what we're going to have are crests, which will be parts of a wave that are going up. And then we're going to have valleys, which are going to be the part of the wave during its oscillation that's down below some arbitrary axis. The amplitude will be the point between this arbitrary axis and the highest point of a crest, or between the axis and the lowest point of a valley. And the distance between the top of a crest to the next crest, we will call that lambda, the wavelength. Lambda looking like an upside down Y or the Greek letter lambda. But if instead of going from a crest to a crest, you could go from the bottom of a valley to a valley, that would also be the wavelength. But you could pick one or the other. So for part A, on the line above this arbitrary axis, draw a light wave with 3 crests and 2 valleys. All right, so our first crest, then a valley, another crest, and a valley, and then ending with a third crest. That checks off. We have 1, 2, 3 crests above this axis and 2 valleys below it. On your graph, choose one section and draw the amplitude and label it as 5 meters. All right. Again, the amplitude, it can be between this arbitrary axis and either the high point of a crest or the low point of an amplitude. I'm just showing both options, but you're welcome to choose at least just one. And it could have been this crest, or this crest, or this valley, or this valley. Doesn't matter. Just choose a point between this arbitrary axis and as far as you can get while still touching the oscillating wave. And then we'll just label it as A for amplitude, and we are given a value, so we'll say A equals 5 meters. If instead of a crest you did the amplitude of a valley, then just have this arrow here, and then A equals 5 meters for the amplitude there. Additionally, it says also choose one section, draw the wavelength lambda as 375 times 10 to the 6th meters. Now, once again, a wavelength is just going from one point of a wave to the next point that has the same height and is at the same point in oscillation. The easiest ones would be either from the top of one crest to the top of the next crest. We can use a line for that and label that as lambda, and then label that equaling 375 times 10 to the 6 meters, or whatever value we're given here. If you don't want to do from a crest to a crest, you also have the option of a valley to a valley, from one valley to the next valley if you have more than one shown, and we can label that as lambda equal to the value that we're given. The units for amplitude and for wavelength are going to be meters or lowercase m. And that's part A. For part B, we're going to be using certain formulas from this chart. And use the formulas from the chart below to determine the wave's following parameters. So of the wave that we just drew, we're going to solve some more parameters for that wave. One of them will be the frequency f, represented in units of hertz, Hz. We'll also solve for the energy E in units of joules, capital J. We'll also solve for the period, capital T, in units of seconds, S. And just as a little check, we'll try to solve for the wave speed, V, in meters per seconds, which is just m divided by s. Some equations that we have available to us is the wave frequency relationship, which just says that for any wave, the wavelength lambda times the frequency f equals the wave speed v. The energy frequency relationship says energy of a wave equals Planck's constant h times the frequency. The period formula is just the period t equals the reciprocal of frequency, or 1 divided by the frequency. The wave speed formula is just the wave speed v equaling the wavelength divided by the period. As far as our speeds for different types of waves, we have the speed of light constant c, where c equals 3 times 10 to that is a typo. That should be times 10 to the 8th. There we go. The speed of light constant c should equal 3 times 10 to the 8th meters per second. And if we were talking about sound, then the speed of sound, well, its value can change depending on the temperature, but typically speaking, the speed of sound represented cs, or c subscript s, is about 343 or 343 meters per second. Now, Planck's constant h, that equals 6.626 times 10 to negative 34 joule seconds. So the unit of energy times the unit of time, joule seconds. Okay. Well, those are the equations we're looking at. And right off the back, let's draw back to part A. It says we're working with a light wave. So anytime that we need speed, we're going to use the speed of light in this example and not the speed of sound. If instead you were working with a sound wave, then you would use this value as the speed for v. But we're working with light, so we'll use v equals 3 times 10 to the 8th meters per second, or wavelength times frequency equals c, in this case, the speed of light. And if we work with that, c equals lambda times frequency. Because we're working with light, we can replace v with c. Solving for the frequency f, that would be the speed divided by the wavelength. Since this is a light wave, the speed is going to equal c, or 3 times 10 to the 8th meters per second. And we were already told in problem A that our wavelength, lambda, is 375 times 10 to 6 meters. If you're doing this in your calculator, your best bet is to have everything in the denominator in parentheses, since we're also multiplying some stuff that are in the parentheses. This way, if you have your entire denominator in parentheses, your calculator knows to have all of this at the bottom. If you don't include your parentheses, then it will divide 3 times 10 to the 8. It will just divide that by 375 instead of by the product of 375 times 10 to the 6th. In any case, just adding parentheses just so that everything gets lopped together where they should be based off of order of operations. Meters per second divided by meters just equals 1 over seconds. This value divided by that value gets us 0.8. So 0.8 inverse seconds. When we're talking about frequency, we change 1 over seconds to the unit hertz. Hertz are just inverse seconds, but that's the unit that we're going to call the unit of frequency. So 0.8 Hz or Hz. And that's the frequency. For energy, the energy of a wave equals Planck's constant times the frequency. Now, Planck's constant, we were told in our chart, is 6.626 times 10 to the negative 34 joules seconds. That's why that number got plugged in here. And we're going to multiply that by the frequency we just solved. So 0.8 hertz. And joules seconds times hertz, or joules seconds times an inverse second, the seconds cancel, and that's why we're just left with J for the unit of energy, or joules. And if we multiply 6.626 times 10 to the negative 34th, and multiply all this by 0.8, that gets us 5.3008 times 10 to the negative 34 joules. Okay. Subpart C asked for the period. Now, according to our formula, the period is just the reciprocal of the frequency. Okay. So taking 1 divided by our frequency, or 1 divided by 0.8 hertz, this is going to be 1 over inverse seconds, which just means that our units are going to be back to seconds. And 1 divided by 0.8 is just 1.25. So the period is 1.25 seconds. And lastly, the wave speed. Even though we were already told we're working with light, which means that we assumed that the speed was 3 times 10 to the 8th, let's just do a check to make sure that the value that we calculated for period makes sense with the value for wavelength we were given all the way at the start. And if we do this, wave speed equaling the wavelength divided by the period, the wavelength was given to us as 375 times 10 to the 6th power in meters. And we're going to divide that by the period 1.25 seconds. And this comes out to 3 times 10 to the 8th meters per second. So, since we got back our speed of light, since we were working with a light wave, that's a pretty good way of saying that the values we calculated along the way, they check out. Definitely frequency and period. Now, based off of rounding choices, this might be close to 3 times 10 to the 8th, and if it's realistically close and your math is pretty understandable, then most likely I'll consider that a correct answer as well. But this part, subpart D, was just a little check to make sure that the answer we got for speed is what we were using all the way at the start, just to make sure that all of our answers were going as they should. In any case, that is our worksheet for our 5th lesson. It is, as always, a pleasure to have you all in class, and I wish you all the best. And just for YouTube's sake, if you would like the video and subscribe to the channel. Saying subscribe usually makes that subscribe button glow like a rainbow. So that's the reason why I'm doing it for this week. In any case, wish you all the best and peace.